cycloadditions. And so these concerted cycloadditions are as follows. A concerted cycloaddition is a reaction in which electron flow occurs in a circle or in a ring-like fashion. And the other thing is that it's bond-making and bond-breaking steps are simultaneous. All right, so electrons are flowing in a ring-like form, and then the bonds are breaking and the bonds are forming at the same time. And so the nature of the electrophile will dictate the size of the ring that forms. Sometimes we'll have 3-membered rings, sometimes we'll have 4-membered rings, sometimes we'll have 5-membered rings. And it also will determine which functional group transformations will occur. So, for example, a 2+1 cycloaddition. The 2 here always indicates that you have a pi CC bond. The 1 is going to indicate that you have one other atom or one other pair of electrons in that ring. And so you're going to form a 5-membered ring in this case. Excuse me, a 3-membered ring in this case. So let's talk about the various types of cycloadditions that we have. This is probably going to take us all week long because there are many, many different types of cycloadditions. The most common type of cycloaddition that you'll see with addition reactions of alkenes is the 2+1 cycloaddition. So let's talk about the 2+1 cycloaddition. All right, so I'm going to label this A. And so we have the first class of cycloadditions known as the 2+1 cycloadditions, and we know that those are going to make a 3-membered ring. The first example is a reaction known as a halogenation reaction. A halogenation reaction, it could be known as a chlorination or a bromination or an iodination reaction, involves the addition of X2, where X is some halogen, across the double bond. Okay, so the halogenation reaction involves a 2+1 cycloaddition in the first step, followed by an SN2. Okay, so how does this work? Well, let's take the case of a bromination. So a bromination is just going to be the addition of bromine across a double bond. And so let's take the example of this one here. So you have a trans alkene and the presence of bromine. And I'm going to tell you that the product of this reaction is the addition of bromine across the double bond to give us a product that looks like this. Okay, and you always get the enantiomer here as well because we didn't start with any stereochemistry. Okay, so let's talk about what's happening in this reaction. Well, the first thing that happens is that you get a, if we rotate the alkene so that it looks like this, we can orient the bromine so that it's going to react with this pi system. Okay, so we have this pi system here above and below the plane, and we can say that as the bromine adds, it's going to add in a 2+1 cycloaddition we have a sigma star bromine-bromine bond. That's going to be our LUMO. Okay, and our HOMO is going to be the pi CC. All right, so this is our LUMO. Okay, so how does this orient? You're going to get a transition state, right, in which you take the alkene, and copy it over, take this alkene, and you're going to orient the bromine so that it's perpendicular. And so the bromine is going to orient itself this way. Now, why does it do that? Well, it does that because they can then grab, the pi CC can then grab the sigma star bromine-bromine bond. So what is the series of arrows that we draw here? Well, you have to follow along. So I'm going to draw it in purple. So the pi CC is going to populate that sigma star BR-BR. When you fully populate the sigma star BR-BR, you break the bromine-bromine bond. And then the lone pairs on bromine are going to back attack the other carbon atom. And so this is a transition state that is forming and breaking those bonds all at the same time. And what you can see is that you're forming a three-membered ring transition state. So this is the cycloaddition part of this mechanism. And so if we draw the net result of that set of arrows, what we will see is that you get a reaction in intermediate, that is known as the bromonium ion. Right? So all the stereochemical information that we had at the beginning will be propagated through to this intermediate. And so because it's concerted, we don't have any bond rotation around that carbon-carbon bond. Bromine's going to be positively charged. Okay, and so the phenyl group on the left is towards us, the phenyl group on the right is back away from us. And so we've got this bromonium ion intermediate. And we also know that this bromonium ion intermediate is delta plus at that carbon atom. And so we can perform a simple SN2 reaction by taking the bromine and attacking via a SN2 reaction that sigma star BR-BR, sigma star carbon bromine, sigma star carbon bromine, and it's going to look like this. Okay, sigma star carbon bromine. It's going to be attacked. You're going to break the carbon-bromine bond, and then those two bromines are going to be added, and you'll notice that they're added in a trans fashion across that double bond. Okay, and so this is the SN2 step of the mechanism. Okay, we already know that the SN2 reaction is a concerted mechanism. The 2+1 is a concerted mechanism. So overall, this is a stereospecific reaction. All the stereochemical information we have in the starter material is propagated through to the product. And if we look at our product, we'll notice that the bromines are going to be trans to one another. And then the phenyl groups, they started trans to one another, and they're going to end trans to one another as well. Okay, another way of showing this mechanism is by simple line angle structures. You can say that the bromine is going to orient like this. If you wanted to draw arrows, attack, loss of bromide, back attack to give us a bromonium ion. Followed by bromine attacking, and it can attack either of those two carbon atoms. Each of them has a sigma star carbon bromine. Let's say that this bromonium ion is a wedged bromonium ion. That means as that bromine attacks, it's going to attack from the back face. And so you're going to have a phenyl group on either side. Bromine is going to be attacked from the back here, which leaves that bromine on the front. Okay? And so this is how this reaction works to give us a trans dibromide. Now in this reaction, you might recall that in the first step, the pi-CC, or as our HOMO, is going to act as a nucleophile and populate the sigma star bromine-bromine, breaking the sigma bromine-bromine bond. At the same time, those lone pairs on bromine will form a bond with the other carbon atom. So this is where you're getting your three-membered ring bridge. We say that the bromonium ion is now bridged, and it's a result. It's a result of this 2+1 cycloaddition. So you might see this known as a bridged bromonium ion. There's actually equal bond formation between both carbon atoms and that bromine. Even though we have to draw this set of arrows that kind of looks like the first carbon is making a bond to the bromine, the reaction is really concerted. All of these bonds are forming and breaking at the same time. In the second step, that bromide anion is going to perform an SN2 reaction by attacking the sigma star carbon bromine. The net result is also stereospecific. And so there's a net anti-addition or trans addition across that double bond to give you a trans dibromide. The fact that we get one product tells us that this is a concerted reaction. It tells us that this is a stereospecific reaction. If it was not a concerted process and the bridged bromonium ion opened up, let's just draw that. If, let's say, this bridged bromonium ion opened up to give us a carbocation, then we could draw the bromide anion attacking from either the front face or the back face. And that gives us two different products. And so the fact that we get only a single product tells us that this bridged bromonium ion does not open up to give us a carbocation. Right? So this is a feature of a lot of the reactions that we're going to come across in cycloaddition chemistry or addition reactions of alkenes, is that you don't get these carbocation intermediates that can then lead to what we call stereochemical scrambling of the products, okay, or racemization. Okay. So bromination of alkenes is a good method of testing a sample for the presence of double bonds, because the brown color of bromine will disappear upon reacting with alkenes to give a dibromide. Another method of bromination is the use of NBS. So let's take this alkene here. So it's a tetrasubstituted alkene, so we don't have any regiochemistry that we need to worry about. And we're going to use NBS as our brominating agent. NBS stands for N-bromosuccinimide, and it has this structure. So this is N-bromosuccinimide. And this reaction proceeds very similarly to the bromination reaction. You're going to have an alkene is going to react with NBS. Instead of populating the sigma star bromine-bromine, this time it's going to populate the sigma star bromine-nitrogen, and you're still going to get a bromonium ion as your intermediate. Okay, I haven't drawn any stereochemistry here because it really doesn't matter, because those are two methyl groups. And so I can then take my succinimide anion, and the succinimide anion will then react in a trans fashion via an SN2 reaction to give us the trans addition of bromine and succinimide across that double bond. Okay, there are other electrophiles that will perform similar mechanisms but have different functional groups. You can think of the reactions of chlorine. We can have NCS. We can have NIS and I2. All of those will perform chlorination or iodination reactions. A couple of important points for chlorinations. There is what we call stereochemical leakage. And this is where the halonium ion, the chloronium ion, actually does open up to give you a carbocation. So you have to be mindful about that. And in the case of iodination reactions, this can really only be done in an intramolecular sense. The reaction is too reversible for an intermolecular reaction, so you have to do it intramolecularly. All right, so this is the halogenation reaction, most commonly a bromination reaction, addition of bromine in a trans fashion across a double bond. A slight variant of this is the second reaction in this series of 2+1 cycloadditions, and that's known as the halohydrin formation reaction. So the question I want to pose here is the following. What if instead of running this reaction in some benign solvent like ether, what if we ran this reaction in the presence of bromine? Presence of bromine in water, excuse me. This reaction is still going to undergo a 2+1 cycloaddition followed by an SN2 reaction, but now you have water in this reaction, which can, since it's solvent, water can outcompete the bromide anion. Okay, so how does this reaction work? Well, the same kind of thing occurs. You're going to get a syn addition of bromine across that double bond to give you a bromonium ion. Okay, so we can draw arrows like this. Right, and we get an intermediate. Let's say this bromine adds from the top face. It gives us a wedged bromonium ion. It, of course, could come from the back face. That could just give you the enantiomer. Let's say that at this point, we could have bromide anion attack, but bromide anion is going to be in much smaller, much lower concentration than just having a water molecule, which is the solvent, compete. And so water can actually undergo an SN2 reaction with one of those two carbon atoms, attack the sigma star carbon bromine, and that's going to give us a product that has bromine sticking up and a protonated alcohol sticking down. This can then undergo deprotonation with, again, water as solvent, or even bromide anion as a weak base, probably just water, does the deprotonation, and then you get as your product this trans addition of water and bromine across the double bond. This is known as the halohydrin. So this is a halohydrin formation reaction. This involves the addition of bromine and water across the double bond. So a slight variant of the bromination reaction. All right, again, we are proceeding via a 2+1 cycloaddition, which is concerted, followed by an SN2 reaction, which is also concerted, and so this is the reason why we get a trans addition of those two groups across this double bond. Now, the other thing we have to be concerned about in this case is when the starter material is no longer symmetrical. So let me just draw in the product here. Notice that we can have this product, or we can have the enantiomer. But what happens if the starting alkene was no longer symmetrical? Well, let's take a look at that. So let's start with an unsymmetric alkene. Let's start with this one. We've seen this kind of reaction scheme before, reactant before, starter material. Let's say we react it now with N-chlorosuccinimide. And let's say we do that in the presence of water. We're going to get a 2+1 cycloaddition again. We can draw in N-chlorosuccinimide. This is the chlorine variant of N-bromosuccinimide. We're going to get a 2+1 cycloaddition to occur, and so we're going to get the chloronium ion. Let's say it adds from the top face again. That's going to make our methyl group go back, and our chlorine is going to be in front. And so here's our transition state. And now we could have chloride attack, or we could have water, which is higher in concentration. But adding water can occur in one of two places. It could occur here, which is the less hindered site, or it could occur here, which is the more delta positive site. And it turns out that the regioselectivity of this reaction is going to be Markovnikov. And so I'll draw this arrow going down here. It's going to give you the product that has water attached to the more delta positive site. Now, why is that more delta positive? Because it's more highly substituted. If that particular carbon atom was a carbocation, it would be a tertiary carbocation versus a secondary carbocation on the top carbon. And so water likes attacking that bottom carbon instead. It likes attacking that more highly substituted carbon. And so let's draw out what this would look like. You would get chloride to go like this. The methyl group would be inverted. It would now become a wedge. And then the alcohol, the protonated alcohol, will be a dash. And so it's still going to be an SN2 reaction. Here's our 2+1. Here's our SN2. But this is one of the cases where the SN2 does not occur at the less hindered site. It doesn't occur on that primary center. Excuse me, the secondary center. It occurs at the tertiary center. And so at this point, you can take a weak base, probably water, does the deprotonation, and that will now give you the product that looks like this. Okay, this is the halohydrin again. But this reaction occurs with Markovnikov regioselectivity. Why does it occur with Markovnikov regioselectivity? Because that nucleophile, that alcohol, that the water, attacked the more delta positive site. So these two things are linked together. And so all halohydrins form with Markovnikov regioselectivity because that water is going to attack the site that is more delta positive. All right, so this is the reason why we use these terms Markovnikov and anti-Markovnikov, because it describes the reactivity, the regioselectivity of these products. And so we can predict the product of this reaction. It's going to be a chloride like this, alcohol here, and methyl group there. Okay, so that's the first couple of 2+1 cycloaddition reactions. We'll have more next time.